So, in the previous class, yesterday, in the previous lecture, we introduced the idea of the induced electric field. What is that? Let me quickly repeat steps which I've done yesterday in order to bring to the naturally to the idea of the induced electric field. So we started with something like this. If you have a loop, conducting loop, right, and we exposed it to the magnetic field. Of course, in this case, there will be flux, and if that magnetic flux changes in time, of course, there will be EMF produced, and there will be current, induced current flowing through this loop, right? Clockwise or counterclockwise, right now, it doesn't matter. So now we have current. And then I ask you, guys, so if there is a current, of course, usually is a consequence of what? So what should we have here? Of course, usually students say potential difference. Yeah, but that's what we have in our Faraday's law, right? So we wanted to go one step deeper. And in order to produce electric current, there must be electric field, period, right? So there must be electric field. And we call that electric field the induced electric field, right? So over here, there's induced electric field, and electric field lines form circles. And at any point, electric field is tangent to the loop, right, at any point. Then the second step which I made, I told you guys, what if I grab this loop and remove it from here, right? What would be different? Obviously, current will disappear because now there is no loop, there's no medium where the current can flow, right? If you remove the loop, of course, current is not there. But what about the electric field? And this is completely not intuitive. Electric field is still here. So this induced electric field is produced, basically, by changing in time magnetic field. Since magnetic field is still here, this space is filled with magnetic field, and that changing in time magnetic field produces this induced electric field, and electric field lines are circles. So presence of the loop is not needed to produce electric field, right? Changing in time magnetic field produces induced electric field. So now we introduced a new type of the electric field. Before, at the beginning of the semester, we had what is called Coulomb electric field, and now we're introducing induced electric field. They're both electric fields, but they have slightly different properties, right? Okay, so that's how we bring into our game this new type of electric field, right? And of course, now what about the formula, the expression which can be used to find that induced electric field? And that can be done from the Faraday's law. We just need to rewrite it in a more general form. We just need to get rid of this EMF. We just need to write it in terms of the electric field. And we've done that transition yesterday, right? Using results from chapter 26. You remember when we build the bridges to move from the electric field to the electric potential, and from the electric potential back to the electric field, right? So as a result, we wrote this Faraday's law. Again, it's still, I'm emphasizing, it's still the same law. We just wrote it in a slightly different form. It's still the same Faraday's law. So integral over the closed loop, this induced electric field dotted with element of the loop ds equals to minus rate of change of the magnetic flux, d phi over dt. Of course, over here, closed integration over closed loop. So that's the general form of the Faraday's law. If you open any book to see Maxwell's equations, one of the equations will be that. This equation will be one of those equations, right? Okay, so and let me write also sort of this important conclusion that changing. Okay, yeah. So look at the structure of this law, and all Maxwell's equations have the same structure. On the right-hand side, we have sources, which produces fields shown on the left-hand side. In this case, effectively, it's a changing in time magnetic field, because inside of that magnetic flux, there is a magnetic field. So changing in time magnetic field produces induced electric field. When we played with Gauss's law, on this side, we had charges. charges, right? And on this side we had a Coulomb electric field. So I could say that these charges produces that Coulomb electric field. Then we played with Ampere's law, and the structure was very similar. On this side we had currents, enclosed currents, right? Those were sources of magnetic field shown on the left hand side. So all those equations have exactly the same structure. Sources on the right hand side, fields on the left hand side. Okay, so now let me write that down. Changing B produces E induced. Right. It's a very as I said in the lecture, kind of mind-blowing probably conclusion back then, I don't know, a couple of 100 years ago, okay, probably less, 120 years ago, that changing in time magnetic field can produce an electric field. It's important. All right, okay, now, let's apply this somewhere, right? Where can we get easily changing in time magnetic field? Of course, yeah, plenty of cases, plenty of situations, but the simplest, right, is solenoid, right? If you drive the current through the solenoid, of course, inside of the solenoid, there will be a uniform magnetic field. And if you start changing current in time, of course, magnetic field inside will be changing in time. Changing in time magnetic field produces induced electric field. It means that inside of this solenoid, there will be magnetic electric field, induced electric field. And electric field lines form circles. Circles, circles, circles. All right. Okay, so now let's discuss the situation. Write down the expression for the induced electric field and direction. How can we find direction of the induced electric field? Okay, so now let me write it down. Okay, probably I will put a new bullet, right? So let's apply this. Which way I wrote it? Okay, for a solenoid. Right. Okay, so let me draw a solenoid over here. Probably it will be something like this, right? So let's say we have enough. So let's say this is my solenoid. Current in, current out. So let's assume that this is current in, here current getting out. And let's say current is what? Is going down. So let's assume that current is going down in time, right? And of course, there will be magnetic field produced. Let's assume that a magnetic field is down, right? So magnetic field. So that will be our B. And what will be, what happens to this B if current is going down? Magnetic field will be also going down.
What's the direction of that blue arrow?
This,
Yes.
you mean this down? Basically, that's how I show that some quantity, the value of the quantity is reducing, is going down.
Okay.
Yeah,
Okay.
but yeah, that's in time. But current flows, of course, through the solenoid, like that.
Okay.
Okay. And so yeah, B also decreases. And now let's draw a top view of this situation, right? So what if your eye, for example, over here, right? And you're looking at this from the top. So let me write top view, right? Okay, you know what? Probably I will use my plate to draw it so that I will have a nice picture. Okay, it should be enough. I will try to clean this plate it's difficult to get rid of these markers. All right. Okay, so it's a top view. So of course, magnetic field you see inside, I mean down. So over here it will be represented by this process. So that's our B, right? Of course, let's say this is radius. This is the center of the solenoid. This is R sub zero. R sub zero radius of the solenoid. So it's a solenoid. Let me show that this is solenoid. And yeah, as I said, changing in time magnetic field produces electric field inside. Inside induced electric field, they form circles. Electric field lines are circles, right? So let me probably let me use blue. All right. Something like this. So these are induced field lines, electric field lines. Okay, A line, one of the lines, right? Okay, and now, of course, let's assume it's at the distance r, at a distance r from the center. Okay, for example, this point. And of course, you can ask two questions. What is the value of this induced electric field? And what's the direction? So how can we answer those two questions? So first, right, about a direction. E induced direction. Very simple. Basically, you don't have to do anything new, right, relative to the previous classes. You need to imagine that over here, you imagine a conducting loop. Imagine a conducting loop. Position it there so that the loop will go through the point in which you're interested in, right? And apply Lenz's rule like we've done in the previous classes. So there is a loop, flux, of course, magnetic field is going down, flux is going down, right? So the loop will be supportive, right? It will start driving the current in such a direction so that the induced magnetic field will be in the same direction as the external magnetic field, right? And then apply right-hand rule, and you will be able to get the correct direction of the induced current, and that is also direction of the induced electric field, because direction of the current and direction of the electric field the same, because you remember we have positive charges. Positive charges give us direction of, okay, motion of positive charges give us direction of the current, right? So in this case, direction of the current gives us induced current through this loop, give us direction of the induced electric field, right? So in this case, have I, okay, of course we can apply that, but I will just write how to find the direction. Imagine a metal loop. Imagine a metal conducting loop and apply Lenz's rule. Right. Okay, very simple. So that's the direction. Now the second part. What about magnitude? E induced magnitude. Okay, this formula should be applied over here. You should integrate over this path, right, with radius r. Integration and the procedure is very similar like we've done applying Ampere's law. Very, very similar, right? If you want to look, you can look at my slides. In one of those slides, I went through that derivation. It's very similar to what we've done applying Gauss's law and then Ampere's law, and the same can be done here. I usually skip that. After some point, I started skipping it. But if you apply that, you will be able to find the expression for the induced magnetic field inside of the solenoid. Okay, let me probably separate this like this. So magnetic field for R smaller than R naught inside. First, inside. And the expression is I induced equals R over 2. R small, it's a radius, it's a distance from the center to the point where you want to know the value of the induced electric field. And times rate of change of the magnetic field. So that's what we will need today. Basically this formula and that fact, how we can find the direction of the induced electric field. But of course, we can also write down the expression for the induced electric field outside of the solenoid. Induced electric field will be non-zero even outside of the solenoid. Again, it can be shown mathematically using this law and integrating it over the circle outside of the solenoid, right? So, but let me write it down. So for R larger or equal than R naught, outside, E induced equals to what? R naught squared over 2R. R sub 0, it's a radius of the solenoid, you see, R sub 0. And again, times rate of change of the magnetic field. Right. Okay, so what we need today, we will need this. And of course, we will need this. Imagine a conducting loop and apply Lenz's rule. So that's we discussed pretty much up to this point in the lecture, but I didn't discuss that in the lecture, right? Because we ran out of time, right? Okay, so now, yeah, maybe I can plot it also. Look, we can plot how induced electric field changes with distance inside and outside of the solenoid. Okay, so I can plot it easily. So let's say we have E induced versus R. So this is R naught, radius of the solenoid. And so first, what happens? Let's assume dB of dt is given. Then first, inside, it grows with R linearly. Right? And then outside, again, R naught is given, dB over dt is given, and then it decays as 1 over R. Right? So here, proportional to R, here it's proportional to 1 over R. So that's how induced electric field. All right. Again, we have sort of like two steps. First, we have current. Something happens in time with current. It produces inside, of course, magnetic field. And since that magnetic field changes in time, electric field, induced electric field will be produced. Don't blame me. God created nature this way. We're just trying to model it. We were just trying to describe it somehow. All right. Okay. So now problems. Let's look at problem 19. It's still the same chapter 30. Problem 19. So what do we have here? Obviously solenoid, because yeah, we don't have any other expressions. So there's a solenoid. Where's my solenoid? Here, right? Some information about the solenoid is given, radius. Then we know how fast magnetic field changes in time of the inside of the solenoid. And then we'll take a proton, positively charged particle, right? And position it with 0 initial velocity at several spots inside of the solenoid. I will show you which spots. And we will need to find acceleration of the proton at the initial moment of time. So that we will position at a certain spot, for example, over here, right? And release it. Initial velocity is 0. And we will need to find the value of acceleration at that moment of time, at the moment of release, right? And then some other spots. Okay, so that's the problem. Now let me give you all the details of the problem. So we have a solenoid and some parameters. Radius is given to, okay, 2 centimeters. Okay, of course, at some point you'll have to convert to meters. Then rate of change of the magnetic field is given. Absolute value. Oi, that's ugly D. Let me change it. dB over dt absolute value equals 0.1 unit. Simple. Just look at what we have here. Tesla divided by seconds, right? All right. Tesla divided by seconds. And what happens with that in time decreases. Then we have a proton. And initial velocity of the proton is 0. And as I said, we need to find acceleration. Okay, let me write that down. Find a acceleration, let me emphasize. Acceleration at points, several points. At points, okay, I will write in a second which points. Let me draw the picture now. And then I will show you which points we will use. Okay, again, I will need to use my plate. I think it should be enough. Right. Yep. So that's the solenoid. This is the center. Of course, this is R. And points where a proton is going to be released. Okay, midway between the center and the edge over here, this will be point A. Then center, point B. Then midway, again, point C. And on the edge, point D. So these 4 points. At 4 points, A, B, C, D. Okay, I think I gave you everything, right? One important piece of information still missing. I didn't give you direction of the magnetic field. Without that, of course, we wouldn't be able to solve the problem. A magnetic field is into the board. So that's B. Okay, now I think everything. Before we start actually solving it, let's discuss again conceptually what happens here, right? We need to understand physics, right? Again, the same steps like we had here. We have solenoid, and most likely current inside of the current through the solenoid changes in time. As a result, magnetic field inside of the solenoid, actually current most likely, definitely current is going down. And as a result, magnetic field is going down, decreases, right? And we know that whenever, it doesn't matter where, if you see magnetic field changing in time, magnetic field, there must be induced magnetic field in that region. Mathematical expression, and here I wrote in words, changing magnetic field, changing in time, right? Here we do have magnetic field, it changes in time. So inside of the solenoid, there must be electric field produced. And electric field lines form circles, right? Okay. And then the charge must interact. Now we have 2 fields, right? We have magnetic field. We have then we'll have electric field, and then of course the charge will interact. And of course, as a result, it will start accelerating, right? We will need to find that acceleration. Okay, so let me now draw a train of thoughts in order to see clearly what I just told you. And again, let's start from the end, from the acceleration. That's what we need to find eventually, right? So let me start. So acceleration, right? So it's the end. And then What do we need to know in order to get information about acceleration? We've done it already many times in this semester, right? You all know, right? It's a Newton's second law. Of course, we will have to apply, and you need to know information about the force acting on the charge, right? So here, of course, you will have to apply Newton's second law, F equals ma, in order to make a transition, right? But which forces should we consider, right? Over here, there will be information about the forces, right? And which forces should we consider in this situation? How many forces so far we had in this course? Two. Two fields, electric field, magnetic field, and as a result, we have two forces, electric force, magnetic force, right? And here we do have magnetic field. And as we discussed, there is a induced electric field. So we have both fields, electric and magnetic. So of course, strictly speaking, we have to consider both of these forces. Okay, let me write that down and analyze what's so special about each of those forces, right? Okay, so let me write down first probably electric force, right? All right, F electric equals to Q times E, right? Electric force. And then magnetic force. Magnetic field is still there, right? So we need to look at that. So now F, okay, which way I wrote it? Just subscript M. Okay, Q and V. You know what? I'm running out of space. I need to get myself more space. Right. F magnetic equals Q V cross B. These two forces. Okay. Of course, here E will be induced electric field. Now, question for you. Think for a second. What can you say about the value of the magnetic force based on what is given? When do we have to find acceleration? You know what? Acceleration at points, these points at the initial moment of time, at t equals 0. I said in words, but I didn't write on the board that important piece of information. We need to find acceleration at the moment of release, at the initial moment of time, t equals 0. What can you say about the velocity of the proton at that moment of time? It's 0. It's 0. So magnetic force is 0. So pretty much the author of this book, all right, simplify our life by giving us this piece of information, V equals 0, so that we don't have to consider this magnetic force. Actually, yeah, we do consider, but it's just 0. So as a result, there will be only electric force acting on the charge. Just basically the author simplified the problem. Otherwise, it will be more complicated, significantly more complicated, right? So now let me write that down. So since V naught equals 0, so this force, okay, let me dump it like this, is 0. Right? Again, at the initial moment of time. But once if a proton starts moving, right, at the next moment of time, of course, there will be two forces. There will be still electric force acting, and magnetic force will start acting. But at the initial moment of time, magnetic force equals 0. But again, once the proton starts moving, okay, the magnetic force will appear immediately. Okay, so that's the second step, right? And now, obviously, we need to get information about the induced electric field, right? In order to get information about the force. So E induced, right? We'll have to get that direction and magnitude. And of course, induced electric field is produced by changing. And you know what? Let me write just dB over dt because I'm running out of space. So dB over dt produces induced magnetic field. Electric field, induced electric field. So that's the train of thought. That's the problem. Right. Okay, so let's do it now, step by step. So we need to get information about induced electric field, and we know how that can be done. Direction, magnitude. Since all 4 points are inside of the solenoid, so of course we will have to use that formula, right? So now direction, E-induced direction, E-induced. Let's start with direction and then magnitude and the rest of the steps, right? Just logically follow. It will look better this way. Okay, so direction. You remember we need to imagine a conducting loop, right? In order to find direction of the, yeah, also, look, once you know direction of the induced electric field, then since charge is positive, it's a proton, direction of the induced electric field give us direction of the electric force. Then, of course, since mass of any object is positive, so direction of this force give us direction of acceleration. Basically, direction of acceleration is determined by the direction of the induced electric field in this particular problem, because we're dealing with the proton. If we had an electron, of course, the situation would be reverse. Okay, so that's why we need to get this direction in order to tell immediately what will be direction of acceleration. Okay, so Lenz's rule. Okay, I can imagine, for example, over here. Right? Can I use this? No, too big. Okay, I have to draw it by hand. So I will imagine a conducting loop over here. So that's my, let me write, imaginary conducting loop. Imaginary conducting loop. Right. Okay, and Lenz's rule, like we've done many times. So area stays the same, right? Area is constant of that conducting loop. Angle is constant. I can make it 0, I can make it pi, right? We've discussed it many times. But magnetic field is decreases. B is going down. So as a result, flux, magnetic flux is going down. So the system becomes supportive, right? It will drive a current in such a direction so that B induced will be in the same direction as B external, right? And as a result, right-hand rule, so in the same direction, it means that I can draw a bunch of crosses into the board. So I have to position my hand like this, right? So this is my loop. So my hand must be positioned like this, and my thumb give us direction of the induced current, which is clockwise, right? So that will be the direction of the induced electric field. Yeah, I just check my notes, clockwise, right? So as a result, I can write, so it will be I induced CW, and then we can add now additional step, direction of the induced electric field, also clockwise. Induced electric field lines, E induced, also CW. So that's what we wanted, right? And since our point A is, okay, maybe I can show the direction sort of like this, like that, like this, like this. And in our points A and C and B, I can easily draw acceleration, direction of acceleration, right? So let me use red. So this will be, again, it's tangent. So that's the acceleration of at point A. Point C, of course, it will be down. So this will be acceleration at point C. And here, acceleration at point D will be also down. Because, yeah, as we've discussed, direction of the induced electric field determines direction of acceleration. So immediately I drew those vectors, directions of acceleration. Okay, so now next step, of course, magnitude.
B is...
Yeah.
What direction is B?
Okay, on purpose, I left it sort of undetermined. And I'm glad that you
Okay.
asked. In a second, you will realize, right? Okay,
Okay.
let me write immediately after this step, right? Let me write down the expression for the induced electric field. We are inside of the solenoid, so we must use this, right? So, okay, magnitude. Let me write magnitude. So E induced will be equal to R over 2 and dB over dt. So that's, of course, the formula which gives us the magnitude of the electric field. Okay, talking about your question, what's the value of R at point B?
0. Oh,
Zero.
okay.
So
I
the
get it. Thank
electric
you.
field will be zero. Electric force will be zero. Acceleration will be zero. That's why I cannot draw the direction of the zero vector, right? That's why I left it, right? Of
Got
course,
it.
I was planning to talk about that somewhere at this point, right? So now it should be better. Okay, so now we are over here. Now let's write down the expression for the force and then expression for the acceleration. Now it's just basically rewriting this formula and adding additional factors. All right, so now let me continue this line. So electric force. Okay, so now I just need to add Q over here. Okay, factor Q. So it will be QR over 2 and dB over dt. Right. And this problem, I think in your homework also. Right. So now we are over here, and now the last step, acceleration. So it's this force divided by the mass, Newton's second law, right? So, and now the last step, so acceleration will be equal F electric divided by the mass, right? So it's exactly now the same, but now I will have to add factor m downstairs in the denominator. So it will be Q times R divided by 2m and rate of change of the magnetic field. Right. So basically, that's the expression for the acceleration in general, right? At any point inside of the solenoid. But since we have 4 particular points, what do we have to do now? We just need to apply a particular R. For A, point A, it's a R capital over 2. Because Q is given, mass of the proton, yeah, open the book, find it. A rate of change of the magnetic field is also given. Everything is given except for pick a particular point, plug the value of that R, you can calculate it. All right, so now we can write, for example, acceleration at point A sub A. And maybe underneath I can write that R small equals to R over 2, R capital over 2. So that's what we have to plug into that. So as a result, it will be Q R over 2 divided by 2m. Don't even think about canceling that 2 and this 2. No, that factor of 2 goes downstairs and will give us 4 in the denominator, right? Times dB over dt. Right. Okay, and of course, don't forget to convert to meters. To centimeters, it's a 2 times 10 to the power of minus 2 meters. Okay, so if you plug numbers, yeah. Oh, you know what? You know what? No, it's good. It's good. It's good. Phew. No, sometimes doubt myself. All right. So this will be, of course, 1 centimeter or 1 times 10 to the power of minus 2. Right? If you divide it by 2. Anyway, so if you plug numbers, which again, as I said, I'm not going to do it, you will end up with 4.8 times 10 to the power of 4. Wow, that's quite an acceleration. Only now I kind of looked at the number and I realized 10 to the power of 4 acceleration. That's quite an acceleration. But of course, we're talking about the world of elementary particles. For them, it's nothing. Right? It's common. Right. And the direction upward. Right. Okay. So that's the answer for point A, now point B, A sub B. So now R is equals to 0, right? Acceleration will be 0, obviously, right? So acceleration equals 0. Then, okay, let me continue writing in the same line because I'm running out of space. Then acceleration at point C. So radius, of course, again, R capital over 2. Of course, you don't have to calculate one more time because it will be the value will be the same as at point A, but downward. Acceleration is downward, right? Here it's up, there it's down. So it's the same as A sub B, but downward. And the last point, D. Oh, where should I write it? All right. Okay, A sub D. So now R small equals to R capital, right? So now we are at the edge of the solenoid. So this is our point D. So of course, it's the radius R small equals R capital. So it will be what? Just acceleration at point A, twice of that. 2 times acceleration at point A. And direction downward. So it will be 2 times acceleration at point A, and again downward. Okay, let me just write down. Running out of space. So that's the problem.
I just want to double check. So mass is the mass of the proton, right?
Yeah, proton, of course, proton. Yeah.
Okay.
That's the proton. And again, don't forget to convert R to meters. Right. So
what was it you were saying about canceling out the 2 in the numerator?
Okay. So they just sometimes I see when I grade a very interesting way of canceling students. Really, sometimes. Right. No, I'm just saying that these 2 factor of 2 you see over there, it will just go in the denominator and will be combined with these 2, right? So I'm just since I saw so many. Yeah.
So is it okay to say QR 4M?
Say it again.
Is it okay to say A of A equals Q times R divided by 4M?
Yeah, 4M divided by 4M. Of course, yeah, that's what I was talking about. Yeah.
Okay.
Because again, as I've seen so many strange cancellations when I grade the exams, right? So now I'm just trying to prevent some finicky stuff, right? Okay, so now I prepared another problem, and probably we will not be able to finish it, but at least let's start and discuss again physics, and then this problem is not in the homework, but just about similar stuff. Okay, I will erase it. Yeah, I'm sure that you followed me closely. Okay, Mike. So problem 18, 3018. Again, solenoid. We have a full description of the solenoid. Geometry is given, everything is given, right? So let me even probably draw this solenoid. Wait, how should I draw it? Okay, let me write it down first. So we have a solenoid. And what is given? Length is 0.2 meter. Okay, 20 centimeters. 0.2 meters. Then diameter is given 4 centimeters. Then number of loops, 400 loops or turns. In this problem it says turns. So pretty much the full description of the solenoid. And even information about how current changes in time is given. All right, so let me draw it over here maybe. All right, so current through the solenoid changes according to this plot. So 1, 2, 3, 4. So it's a 0.1, 0.2, 0.3, 0.4. This is time in seconds. And this is current, of course, in amps. And current changes like this. So up to this point, current is growing linearly. Then it stays constant up to this point. And then it goes down to 0.4. Okay, not completely straight lines, but okay. Okay, so what do we need to plot? We need to plot how induced electric field, E induced, changes with time at point R equals A equals to what? 1 centimeter. Right. So you see, radius is 2 centimeters. So this is diameter, but of course radius is 2 centimeters. And we need to analyze the point, which is the midpoint. It's like in the previous problem, right? Point A and point C were midpoints. So basically, we need to plot what happens with the induced electric field inside of the solenoid at the midpoint. Right? Okay, so again, physics, what happens? We have a solenoid, full information. This point is inside of the solenoid, right? Inside of the solenoid, so we're inside. Since current, you see, it's not constant, it changes. It changes, right, with time. Of course, we will have to analyze 3 different regions, right? So this will be region number 1, this will be region number 2, and this will be region number 3. Of course, we'll have to analyze 3 regions separately. But anyway, in general, current is not constant. As a result, current is not constant. Magnetic field inside of the solenoid changes in time. So there's a dB over dt. And whenever you have areas where magnetic field changes in time, induced electric field will be produced. God's creation, right? So it means that inside of this solenoid, again, we will have induced electric field, like we just discussed in the previous problem, and with circular electric field lines, right? So, and we need to plot actually magnitude. So in this case, in this problem, we don't care about the direction. So the problem asked about electric field strength. Strength is a magnitude, right? Okay, so now let me again draw sort of like a train of thoughts. And I will start from the very beginning. So current changes, I changes. The plot. Of course, as a result, magnetic field of the solenoid, okay, magnetic field of a solenoid also changes. And changing in time magnetic field produces electric field, induced electric field, E induced. So, and that's what we need to find eventually. Again, at point A, at R equals to A, at this point. Right. Okay, and what else we can write? So how can we complete this step? Can we find magnetic field inside of the solenoid? For you, it should be now a piece of cake, right? Let me just a second, wait, a minute, right? it's your quiz number 5. You can easily find the magnetic field inside of the solenoid. So it will be B equals mu naught N times I. Right, in order to complete that step. And then, since you know how current changes, you can see how magnetic field will be changing in time, right? Most likely I will just send you my notes, right, in order to see the whole problem, right? I'm just trying to discuss physics, right? So as a result, you will know how magnetic field changes in time, and then of course, in order to get information about induced electric field, we have to use the same formula, because we are inside of the solenoid. R equals 1 centimeters. It's inside of the solenoid. So now this step must be completed using this formula. I in E induced equals to R over 2 and dB over dt, right? So this will go over there, right? And basically, you will have to do what? You will see, you will just need to find the slope of this curve, part of the curve, in order to see what happens with the magnetic field in time. Then slope of that curve, that part of the curve, it will be 0, right? And then the slope of that part of the curve, again, in order to see what happens to the current. And then once you know, in order to see what happens to the magnetic field in time. And then you can use that, how that magnetic field changes in time can be used over there in order to see what happens with the induced electric field. Okay, this problem is even easier than the previous one. Okay, since we ran out of time, I will scan and send you my solutions. This problem is not on your homework, the previous one is, right? But just for practice, we can look at that. Right? Physics, we basically discussed what happens over here. Right? The rest is just you need to carefully get through the details.